Example 2, using the Taylor series. Here is the Taylor series. Remember, if a equals 0, that disappears, this becomes 0, and we have the Maclaurin series. Here is the first 4 terms written down from the Taylor series. So just remind yourself how that all works, and we're going to use this Taylor series to try now to write down the power series of the log x function. It doesn't exist when a equals 0, so we can't use the Maclaurin series, so we're going to let a equal 1 and work out what is power series. So let's go. Remember, this is the standard differential for the log function. The differential of log x is 1 over x, or x to the minus 1. Think of it like that for successive differentials. What I want you to do now is to take the first 4. So what's the value of the function log x? What we want now is what is that value when a equals 1. So work that out. Then find the derivative of log x. Put the answer here. What's that at when x equals 1? And so on. What's the second derivative? What's that when x equals 1? And so on. Go down to the third or fourth derivative, and by then you should start to see a pattern. So what I want you to do then is try and write down what that term and that term is without actually working out the differential, and then go back and work out the differential and see if you're right, and also see how the pattern is arrived at. And then after that, look for a term for the nth derivative. Can you write a general expression? Remembering if signs are changing, positive, negative, that we've used before is true. Minus 1 to the power n is either plus or minus 1 depending on the value of n. So try and write down this general expression here. Have a go. You can pause. I'll give the answers now, and you can pause at any point and see if you've got it right, and then maybe try and carry on. Okay, so the function is log x, log of 1 is 0. The first differential is 1 over x, or x to the minus 1. The first derivative at 1 when x is 1 is just 1. The second derivative is minus 1 x to the minus 2, so minus x to the minus 2. If I look at letting x equal 1, then that's just going to be negative 1. The third derivative, minus 2 times minus 1 is plus 2. X to the minus 3. Letting x equal 1, plus 2. We can think of this as like a factorial. Might help us to see the pattern. Next one, minus 3 times 2. X to the minus 4. Minus 3 times 2 times 1 if you like. So hopefully we can start to see a pattern now. If I look at this, this is a factorial, 3 times 2 times 1. That's 3 factorial. This is 2 factorial. That could be 1 factorial. So what's the pattern? If I've got the fourth derivative, I'm having the third factorial. If I've got the third derivative, I want 2 factorial. If I've got the second derivative, I want 1 factorial. If I've got the first derivative, I want 0 factorial. Oh, well, that's okay, because 0 factorial is defined as 1, so that's all right. It just doesn't work with this, so we'll have to consider that later. So what can I do now to write down what the next 2 term is? Well, let's take one off. The fifth derivative is 4. It was plus before, so that must be 4 factorial. The next derivative is a 6th derivative, so now minus 5 factorial. So that's the next one. And if I do the differentials, I can see that that works. Minus 4 times minus, so it's minus 4 times minus is plus 4 times 3 times 2. And we can hopefully you can see now why the factorial comes in. Whenever you do successive differentials, the factorial often appears. Minus 5 times 4 times 3 times 2, x to the minus 6. So what about the nth derivative then? Well, it's just whatever n is minus 1 factorial. That's easy enough. The only problem is the sign. So if I look at this one here, the 6th derivative, so if I were to let n equals 6 in here, minus 1 to the power 6 is positive, but I want a negative. So instead of thinking it as being the 6, I just think of adding 1 and making it 7. That will make it odd. So if I put in front minus 1 to a power n plus 1, whatever n is, add 1, that'll make it odd if it's even, or even if it was odd, and I will then have the correct sign. So that's what I want for my general nth derivative. So now I can put these back into the Taylor series. What I'm after, if I look at the Taylor series, is this, that nth derivative at a. So a is 1 in this case. So I know what the nth derivative is at a. It's this. So I can now write my log function as the sum. Now, what about our problem when n equals 0, that first term? I'm just going to have to write down what that first term is. So that's going to be whatever the first term is, 0 plus, and then, right, let's go from n equals 1 to infinity now. So I then put in this Taylor series, but instead of this I'm going to replace it with this, which was the expression for the nth derivative. But looking at it, what I've got on top here is n minus 1 factorial, and underneath n factorial. So if I were to think of an example, for example, this was 4 factorial, and this was 5 factorial, then in fact the 4 factorial will cancel everything except the 5, so I'm just left with n. So an expression for the log function, the log power function, will be this. Log x can be written as a power series, n equals 1 to infinity, ignoring that first term, which is just 0 anyway, minus 1 to the power n plus 1, that's this bit, but now I've just got underneath n, and then times by x minus 1 to the power n. So that is our expression. And I can think of that now about writing down what the first few terms in this power series is. So I'll just, again, you can just pause it here and try and write down what the first few terms is in this series. So here we have, hopefully you got these first 4 terms. X minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. And we can now see a pattern, and we can carry on writing as many terms as we want. Finally, if we put into autograph, which I've done, the first few terms in this series here, then I can plot the functions and see how closely it follows our function. This is, the blue one on here, is the log function. You can see it doesn't exist at 0, so that's why we let a equal 1. And if you look at when x equals 1 at this point here, then that's where our power series is being investigated, and we can see that the red curve follows it between these limits. So it's reasonably accurate between those 2 points. And the more terms we add, the more closely this function will follow the line. So the further away from point a equals, or where a equals 1, we can actually use the power series to represent our log function. Okay.